In this video, we will be talking about the normal distribution. Our learning objectives will be to identify characteristics of a dataset that is normally distributed. We will learn how to apply the empirical rule. We will learn how to compute z-scores and use them to compare values from different datasets. And then we will learn how to use a table and z-scores to find areas under the standard normal distribution. So let's dive in. Back in section 11.2, we were talking about how to collect data and present it graphically. And one of the tools that we went over in that section was the histogram. If you don't remember that, I would encourage you to maybe go back and review that video or that section just to familiarize yourself with the idea of the histogram, because it's an important concept for this section as well. Suppose a researcher selects a random sample of 100 adult women, measures their heights, and constructs a histogram. The researcher would probably get a graph similar to the one shown in figure 11.9a. If the researcher increases the sample size and decreases the width of the classes, the histograms will look like the ones shown in 11.9b and 11.9c. Finally, if it were possible to measure the exact heights of all adult females in the United States and plot them, the histogram would approach what is called the normal distribution, which is shown in figure 11.9d. This distribution is also known as a bell curve or a Gaussian distribution, named for the German mathematician Carl Friedrich Gauss, who derived its equation. So a official kind of definition of a normal distribution, it's a probability distribution that plots all of its values in a symmetrical fashion, and most of the results are situated around the probability's mean. It's called a normal distribution. Values are equally likely to plot either above or below the mean. Grouping takes place at values that are close to the mean and then tails off symmetrically away from the mean. Next, we'll highlight some of the important features of a normal distribution, which in turn gives us the key features of any data set that is normally distributed. So here's some of the key properties of a normal distribution. First of all, the value in the middle of the distribution, which appears most often in the sample, is the mean. Okay, so the mean is right in the middle, corresponding also to the highest peak. The distribution is symmetric about the mean. This means that the graph has two halves that are mirror images on either side of the mean value. 3, this is the key fact, the area under any portion of the curve is the percentage, in decimal form, of data values that fall between the values that begin and end that region. And then 4, the total area under the entire curve is 1. Let's explore property 3 from the above box, because it's really what makes normal distributions so useful in analyzing data. Example 1 here, getting information from a normal curve. The graph below shows a normal distribution for heights of women in the United States. The numbers on the horizontal axis are heights in inches, and some areas are labeled for reference. Right, we've got the area between 57.4 and 59.1 labeled, and then also the area between 63.7 and 66. First question, what is the mean height? Okay, let's answer that down here. The mean is the value in the very center of a normal distribution. Okay, the mean is the value in the center. Okay. And it corresponds to the value that appears most often as well. Okay. So this would be the highest point on the graph. The height of the graph represents the frequency. And it's labeled 63.7 right here. Okay, so the mean height for American women is 63.7 inches. Okay, based off of the graph. I can say the mean height for American women is 63.7 inches. And again, I know that because it is the value that is right in the center, in the middle of my normal distribution. Second question, what percentage of women are between 57.4 and 59.1 inches tall? This is what that third property in the colored box is about, the third property here. The area under any portion of the curve is the percentage in decimal form of data values that fall between the values that begin and end that region. Okay, so what that property says, based off of this normal distribution here, the area under the normal graph between 57.4 and 59.1 is 0.034. This is the decimal form of the percentage of data values that fall in that range. So to convert 0.034 to percent form, to do that, what we need to do is move the decimal place 2 points to the right and then put a percent sign in front of it. Basically, multiply it by 100%. And if we do that, we get 3.4%. Okay. So we could say 3.4% of American women have heights between 57.4 inches and 59.1 inches. Okay, C. If there are 31,806 women at a stadium concert, how many of them would you expect to be between 63.7 and 66 inches tall? This is kind of a very similar question as the previous one, but with a twist. It asks for the number of women, not a percentage. But we can find that number by first finding a percentage. So in this case, the area under that portion of the graph, right, the portion between 63.7 and 66 is 0.303. So that means we would expect 30.3% of women to have heights between 63.7 and 66 inches. In particular, we would expect 30.3% of the women at the concert to have a height in that range. So we need to find 30.3% of 31,806. To find that, we leave the percentage in decimal form and we multiply it by the number. So it's 0.303 multiplied by 31,806. And that works out to be, we're talking about humans, right? You can't have a fraction of a human. So what we should do is we should round this number to the nearest whole number. And when you round it to the nearest whole number, you get 9,637. Okay. So we would expect about 9,637 women of the 31,806 women at the concert to have heights between 63.7 and 66 inches tall. Okay, moving on. So now we know that if we have data values that are normally distributed, and if we can find the area under portions of the graph, we can find the percentage of data values that fall in a certain range. That leads to the big question: how in the world do you find areas under the graph, right? In the example we just looked at, 2 of the areas were given to us, right? So there are methods available for finding those areas. But in this example, those areas were given to us. We were not asked to find them. They were just given to us, right? So how do you figure out what the areas are? How do we figure out that the area between 63.7 and 66 is actually 0.303, for example? Okay. So we're going to look at a few techniques for finding areas. The first one is to introduce this rule called the empirical rule. It is a known rule that allows us to quickly find a range in which most of the data values fall. The empirical rule says that when data are normally distributed, approximately 68% of the values are within 1 standard deviation of the mean. Approximately 95% of the values are within 2 standard deviations of the mean. And approximately 99.7%, almost all of the data values, are within 3 standard deviations of the mean. Figure 1110 here is an illustration of the empirical rule, right? So the mean is right in the center. About 68% of the data is within 1 standard deviation. About 95% is within 2 standard deviations. And about 99.7% is within 3 standard deviations of the mean. This rule allows us to also find areas, a few different areas under the curve, specifically the areas corresponding to just 1, 2, and 3 standard deviations above or below the mean. So let's look at an example where we use the empirical rule. Example 2. According to the website answerbag.com, the mean height for male humans is 5 feet 9.3 inches, with a standard deviation of 2.8 inches. If this is accurate, out of 1,000 randomly selected men, how many would you expect to be between 5 feet 6.5 inches and 6 feet 0.1 inches? Okay. So let's think about this a little bit. The standard deviation here is 2.8 inches. Okay. So we have a mean height of 5 feet 9.3 inches. If I take the 9.3 inches right here, and I subtract the standard deviation, which is 2.8 inches, I get 6.5. Okay. And if I take the 9.3 inches corresponding to the mean, and I add the standard deviation of 2.8, I get 11, what did I get? 12.1. Is that right? 11. Yeah. So 12.1 inches, which is basically 1.1 feet, right? What I'm basically trying to point out is that the boundaries of this interval, the lower boundary, 5 feet 6.5 inches, and the upper boundary, 6 feet 0.1 inches, these are the values that are exactly 1 standard deviation below the mean and 1 standard deviation above the mean. Okay? And so the empirical rule tells us that about 68% of the data falls between this value and this value. Okay? So that means if we have 1,000 randomly selected men, how many would you expect to be between 5 feet 6.5 inches and 6 feet 0.1 inches? You would expect about 68% to fall within that range. As far as an exact number, you would take 68% as a decimal and multiply it by 1,000, which is about 680. Okay. So you would expect about 680 of the 1,000 randomly selected men to have heights between 5 feet 6.5 inches and 6 feet 0.1 inches. And that's because this represents the data that is within 1 standard deviation of the mean. Now, we were able to answer the questions in example 2 because the values we were interested in just happened to be exactly within 1 standard deviation of the mean. We could do something similar if we had data that was exactly 2 standard deviations of the mean, right, or exactly 3. But what if we wanted to know how many men you would expect to be between 5 feet 10 inches and 6 feet 3 inches? We would need to be able to find the area under the graph for that exact situation. These endpoints of this interval are not within an exact 1, 2, or 3 standard deviations of the mean. So that makes it difficult to find the area. What if we decide a different situation, right? We want to try to figure out how many people we would expect to have an IQ between 90 and 105. So we're dealing with 2 different scenarios here. One, we're dealing with heights. One, we're dealing with IQs. Both of these would be data sets that are normally distributed, but the mean would be different. The standard deviation would be different, right? So not all normal curves are created equal. They're all bell-shaped and symmetric. That's true. But different normal curves have different means, different standard deviations. Some of them are wider, some of them are narrower, right? So it's pretty much impossible to have a method for finding an area under every possible normal curve, right? So we're stuck with a similar problem with the graph, and area calculations will be different for every curve, right? So the point here is that while all normally distributed data have the same general shape for their graph, areas under portions of the graph depend on how tall the curve is and how spread out it is. These characteristics, in turn, depend on what the mean and standard deviation are for that particular set. This would require a different set of extremely difficult area calculations for every individual situation involving normally distributed data. Ouch, right? We just can't really do that. Fortunately, statisticians found a way to work around this problem. The areas have all been calculated. The hard work has been done for us for a simple normal distribution. The simple normal distribution is one that has a mean of 0 and a standard deviation of 1. And then a procedure was developed to apply those areas to other distributions. So this special distribution is called the standard normal distribution. The standard normal distribution is the normal distribution that has a mean of 0 and a standard deviation of 1. Here is a picture, figure 1111, that shows the standard normal distribution. The values under the curve shown in this figure indicate the proportion of area in each section. Right, so this picture looks quite similar to the one we saw when we introduced the empirical rule up here, except for this one, instead of writing in, so X bar is the symbol for our mean, right? And then we've got these intervals corresponding to the number of standard deviations. Down here we put in some actual numbers, right? Remember, the mean is the number in the middle. The standard deviation is 1. So 1 standard deviation above the mean would just be 0 plus 1, which is 1. one standard deviation below the mean would be 0 minus 1, which is negative 1. Two standard deviations above the mean would be 0 plus 2, right, which is 2. Two standard deviations below the mean would be 0 minus 2, which is negative 2, and so on. So, since area calculations for normal curves are really difficult, tables have been compiled that list areas under certain portions of the standard normal curve. But they work only for data with a mean of 0 and a standard deviation of 1, the standard normal distribution. So we will apply a clever trick to change any normal distribution into one with a mean of 0 and a standard deviation of 1. To do this, we will find the z-scores for given data values. For a data value with a sample mean x bar and standard deviation s, the z-score is given by this formula. You take the data value, you subtract the mean, and you divide by the standard deviation. Right? Verbally, to find a z-score, you just take the data value, subtract the mean, and then divide the result by the standard deviation. A couple of notes about z-scores. A data point is greater than the mean if the z-score is positive, and less than the mean if the z-score is negative. Z-scores are typically rounded to 2 decimal places. And the z-score for a data value, it's simply a measure of how many standard deviations above or below the mean that it is. I mean, you can kind of see that in the calculation. When I take the data value and subtract the mean, I'm finding the distance between that data value and the mean. And when I divide that distance by the standard deviation, I am then expressing this distance in terms of numbers of standard deviations, right? So it tells me how many standard deviations away from the mean a data value falls. Let's go over a few examples. First of all, just computing a z-score. Based on the information in example 2, find the z-score for a man who is 6 feet 4 inches tall and describe what it tells us. Okay. Okay, so in example 2, we were told that the mean height we'll just call it x bar, was 5 feet 9.3 inches. Okay. Let's make this easy by expressing this number in terms of just one set of units. Instead of feet and inches, let's express it only in terms of inches. 5 feet, let's convert that to inches. There are 12 inches in a foot, so 5 times 12 is 60 inches. Okay. 60 plus 9.3 equals 69.3 inches. Okay. So x bar is 69.3 inches. All right. My standard deviation, S, is 2.8 inches. Okay. And we want to find the z-score for a man who is 6 feet 4 inches tall. So 6 feet 4 inches. I want to convert that into only inches as well. Okay. So for the 6 feet, I will take 6 times 12, which is equal to 72. 72 plus 4 is equal to 76 inches. So that's my value of x. My x value is 76 inches. So my z-score is x minus x bar over s. My value of x is 76 inches. My value of x bar is 69.3 inches. And my standard deviation was 2.8 inches. This works out to be about 2.39 when I round it to 2 decimal places. So what does that mean? It means that the data value, 76 inches or 6 feet 4 inches, is 2.39 standard deviations above the mean. So somebody who's 6 feet 4 inches is actually kind of significantly above average. Okay, because it's 2.39 standard deviations above the mean. Remember from the empirical rule, it says that for any normally distributed data set, you'd expect about 95% of your data to be within 2 standard deviations of the mean. Right? So 95% of your data would have z-scores between -2 and +2. Which means to have a data value with a z-score of 2.39 is somewhat unusual, right? Based off of kind of putting that into perspective a little bit. Let's look at another example, using z-scores to compare standardized test scores. As you probably know, there are 2 main companies that offer standardized college entrance exams, ACT and SAT. Since each has a completely different scoring scale, it's really difficult to compare the scores of students that took different exams. One year, the ACT had a mean score of 21.2 and a standard deviation of 5.1. That same year, the SAT had a mean score of 1,498 and a standard deviation of 347. Suppose that a scholarship committee is considering 2 students, one who scored 26 on the ACT and another who scored 1,800 on the SAT. Both are pretty good scores. They're both above average scores. But which one is better? We can't just compare them to each other because the scale for each of the 2 exams is different. Okay. But what we can do, since we know the mean and standard deviation for each, we can compute the z-scores for each one. And this will allow us to decide which student did better relative to the others who took the same test, right? Which one is actually more above average, right? So let's calculate the 2 z-scores. For the ACT, my z-score, so my x value would be the student who got a 26. So that's my value of x. My mean would be the mean ACT score, which is 21.2. And I divide by the standard deviation of those who took the ACT, which is 5.1. Okay, and this works out to be about 0.94, which means the student who scored a 26 on the ACT was about 0.94 standard deviations above the mean, almost 1 standard deviation above the mean. SAT, my value of x is the one student who scored an 1,800 on the ACT. And then I subtract the mean, which is 1,498. And I divide by the standard deviation, which is 347. Okay, and that works out to be about 0.87. So while I cannot compare the 2 scores directly to each other, I can't compare the ACT score of 26 to an 1,800 on the SAT, I can directly compare the z-scores, right? Because by doing this, I've kind of standardized these 2 and put them on a scale, the same scale that can be compared, right? So the student with the 26 on the ACT did better because their score is 0.94 standard deviations above the mean, while the student who scored 1,800 on the SAT is 0.87 standard deviations above the mean, right? Both decent, but the ACT student did slightly better. Another way that we will use z-scores is to find areas under a normal curve that using only areas under a standard normal curve. And these can be read from a table, kind of like table 11.3. We'll also learn, you can also use technology to find these areas. We won't delve into that a whole lot in this class, but graphing calculators, Excel are all tools that can also be used to find areas. The primary tool that we're going to use in this section is a table, which there will be a kind of a small version of the table in these lecture notes, which we'll see in a moment, but there's also a longer version of the table in your book. So in the remainder of this section, we are going to focus on simply finding areas under a normal curve. For now, we'll find areas corresponding to z-scores. Using table 11.3, which appears on the next page of these notes. We'll take a look at it in just a moment. And also the following key facts. The area under any normal curve is divided into two equal halves at the mean. Each of the halves has an area of 0.5, right? So you draw a vertical line right through the mean of a normal distribution. The area to the left is exactly the same as the area to the right. Because of the symmetry of the curve, they both have an area of 0.5. They're both half the area. Okay. The area between a z-score of 0 and a positive z-score is the same as the area between a z-score of 0 and the negative of that z-score. Remember, the z-score of 0 sits right in the middle. It corresponds to the mean of the standard normal distribution. Each of the facts in the box above is a consequence of the fact that normal distributions are symmetric about the mean. Examples 3, 4, and 5 will illustrate how to find areas under a normal curve. First of all, let's just take a look at table 11.3 right here. Okay. This table gives areas under a normal distribution curve between z-scores of 0 and a positive value of z, right? So we've got z-scores ranging from a low of 0 up to a high of 3.25. And the column labeled A, that gives your area, right? So let's just choose a random value. If we have a z-score of 0.9, the area there is 0.316. You can kind of look at this normal curve down here for reference, right? There's kind of a generic shaded area there. The areas given are the area between the mean and the z-score, right? So this 0.316 area, this would be the area between the 0 and 0.9. If this z-score was 0.9, the shaded area there would be 0.316, okay? If this z-score was 2.05, the shaded area would be 0.48, okay? If this z-score here were, I don't know, 2.5, the shaded area would be 0.494. What about a negative z-score, right? What if you had a z-score of, say, negative 1.05? Well, because of the symmetry of the curve, the areas are the same, right? So if you had a negative z-score down here, this area would be the same as this area, right? Because the curve is symmetric, right? So if you're trying to find the area between, say, maybe a z-score of negative 1 and the middle, you can just take the absolute value. You can just turn it to a positive z-score and look up the area, because the areas will be the same, right? Just a note, an area table with more values can be found in Appendix A of your textbook, I believe. If you're doing your homework on ALEKS, on the problems that require a table, there should be a link directly from the homework assignment to open up a version of this table, probably a more extensive version of this table, the one that appears in the appendix of your textbook. Okay. So again, how to use the table. The value in the A column of the table is the center under the standard normal curve between z equals 0 and each given positive value of z. So let's do a few examples. we want to find the area between two z-scores. We want to find the area under the standard normal distribution, first of all, between z equals 1.55 and z equals 2.25. Okay. A picture is always helpful here. Okay, we've got a normal distribution. This is my standard normal distribution, which means the middle is 0. 1.55 is going to be somewhere over here. 2.25 is going to be even farther to the right, right? So we're trying to find this area. Okay. So what can the table tell us? Well, let's start with the 1.55 value. If I go up here and find the z-score 1.55, what area does that correspond to? It corresponds to an area of 0.439. That area is this area on my table right here. Okay, so this area is 0.439. If I look up 2.225, that is right here. The corresponding area is 0.488. Okay, that is going to be this area. Okay, 0.488. What we want is the shaded area, right? The area in between 1.55 and 2.225. To find that area, to find the shaded area, we can take the larger of these two areas, the 0.488 value, and then if I remove the smaller area, what I'm left with is the shaded area. So I can subtract the smaller area, which is 0.439, and I'm left with 0.049. Okay. So 0.049, this is the area, that's this area, right? Sorry. The shaded area, what I want is 0.049. It's the area between the z-scores 1.55 and 2.25. Okay. Let's see if we can do the other ones. B. The z-score between, or the area between negative 0.6 and negative 1.35. Okay. Again, zeros in the middle. Negative 0.6 would be something like there. Negative 1.35 would be about there. Oops. These numbers aren't showing up real well. Let's see if I can do a slightly better job here, maybe. Negative 1.35. Okay, so again, let's just kind of shade the area we want. We want this area. So I can do something similar, right? The fact that I'm dealing with negative z-scores shouldn't throw me off too much, because the area, just if I think about the positive 0.6, this area right here is going to be exactly the same as this area right here, right? The area to the right of a negative z-score is exactly the same as the area to the left of a positive z-score because of the symmetry of the curve. So what I can do is I can go to my table and I can just kind of ignore the negative signs and just focus on the value itself. So I have negative 0.6. Let's just flip that to a positive. The corresponding area there is 0.226. Okay, so 0.226 is this area, 0.226. And then I have negative 1.35. Flip that to a positive. That has an area of 0.412. Okay, so 0.412 is this area. Sorry, 0.412. So the area I want, the shaded area, can be found by taking 0.412 and subtracting the smaller area, 0.226. And that gives me 0.186. Okay? So 0.186 is the area between the z-scores of negative 1.35 and negative 0.06. Okay. See if I can do the last one over here. Okay, again, we're centered over 0. For C, we're trying to find the area between z-scores of negative 1.75, which is down here, and positive 1.5, which is up here. Okay. Okay, so what I can do is I can find this area and this area separately using the table, and then by adding those together, I get the total area that I want, right? So this area can be found by going to my table. My z-score is negative 1.75. So change that to a positive 1.75. My area is 0.46. Okay, so this area is 0.460. This area, I've got a z-score of 1.5 right here. 1.5, and the area there is 0.433. Okay, so this has an area of 0.433. The area I want is this total area, kind of shade it there, which is going to be the sum of these two areas. Okay, so 0.460 plus 0.433 equals 0.893. Okay, so the total shaded area there is 0.893. When we want to find the area to the right or left of a single z-score, we will use the fact that the area under half of the curve is exactly 0.5. Okay, so that's what we'll do in this next example. We want to find A, the area to the right of z equals 1.7, and B, the area to the right of z equals negative 0.95. Okay, let's take these one at a time. A, we're centered over 0. My z-score is 1.70. That shaded area is what I want to know. What the table can give me is this area bounded by the two arrows there. Okay, but remember that this area plus this area, they add up to equal 0.5, right? Half of the total area. So what my strategy then will be to find this area from the table and then subtract this area from 0.5, and that will give me the shaded area right here. Okay, so let's find this area. My z-score is 1.7. If I go up to the table, my z-score is 1.7. There's my area. It is 0.455. So I will subtract 0.455 from 0.5. Okay, so that will be 0.5 minus 0.455 is equal to 0.045. So the shaded area right here represents 0.045. Okay. B, we want to find the area to the right of negative 0.95. Again, it's always helpful to sketch a picture for all of these, okay? We're centered over 0. Negative 0.95 is over here, okay? I want to find the total area to the right of the curve. And I'm going to do that by finding two areas. Well, first of all, I know that this area over here, this area represents 0.5. It's half, right? Half the area of the curve. This area right here, I can find from the table. So I go over to my table. My z-score is negative 0.95. I'll just ignore that negative sign, focus on positive 0.95. There's my area, 0.329, okay? 0.329. If I add these areas together, I get the total area to the right, which I'll kind of shade. That's the area I'm trying to find. Okay, so it's going to be 0.5 plus 0.329, which equals 0.829. Okay, so that's the area to the right of the z-score, negative 0.95. Example 7, finding the area to the left of a z-score. For these examples, we want to find the total area under the standard normal curve to the left of z equals negative 2.2 and to the left of z equals 1.95. Again, let's take each of these one by one and sketch a picture. Okay? Zero's in the middle. Negative 2.2 is down here somewhere. I want to find this area down here. Remember that, just do this, these two areas combined is half of the total area, right? Half the curve. This area right here, I can find from the table. Let's do that. My z-score is negative 2.2. I'm going to ignore that negative sign. I'm just going to focus on the z-score 2.2. And there's the area, 0.486. Okay. 0.486. So the area to the left, which I will shade, that area, can be found by taking the 0.5, taking away this area, right? Subtracting 0.486 from 0.5. Okay, so if I do that, 0.5 minus 0.486 equals 0.014. Okay? And then B, the area to the left of z equals z equals positive 1.95. Okay, here's my standard normal curve, centered over 0. Positive 1.95 is over here. Okay? Okay, what I can say is that this area right here is 0.5. And this area right here I can find from the table. Okay? My z-score is 1.95. So let's come back up to my table. 1.95 is right here. The corresponding area is 0.474. Okay? So this is 0.474. So the total area to the left, which I will shade, is found by taking 0.5, 0.474, and adding them together. Okay. So 0.5 plus 0.474 is equal to 0.974. So 0.974, that is the area to the left of the z-score 1.95. And that wraps up this section. So get started on your homework in ALEKS, and of course feel free to reach out anytime if you have questions. But thank you for watching.